Hey everybody, today we're going to be talking about engine design and theory and also the operation of an engine. So we're going to do twofold here. I'm going to give kind of an overview of engine design on automobiles, and it kind of can fold over to heavy duty equipment too, which I'll be doing another video on diesel design also. So I'm going to start off with gasoline, which is some of your gaseous fuels like gasoline, CNG, um, LPG, and basically your gaseous fuels. So let's go ahead and get started. I'm going to go ahead and share a PowerPoint with you, and hopefully you'll be this will help you understand how an engine actually operates and how we actually control some of it, and how it operates, like I said before. And we'll go ahead and get started here. So you should be seeing a PowerPoint in front of you right now. I like to use PowerPoints to kind of emphasize what I'm talking about and show pictures. So right now, I do want to say that there is talk about diesel engines going away and possibly gasoline engines going away, or a limited part of it. And there is going to be some struggles if that happens because of the availability of gasoline, one, and we're talking, what I'm trying to get into is electric vehicles, and I'll have another video on that fairly soon. But when it comes to electric vehicles, we still don't have the infrastructure that we need to have. Where you can find a gas station just about anywhere, within a mile radius of your house. Usually, I'm not saying all states have it this way, but here in California, it's pretty easy. So, kind of starting off, the engines can be classified by many characteristics. So, when we look at it and classify an engine, and this is just general, and I'm not talking about uh, actually, getting really down to the nitty gritty. We're just talking in general terms. And you have, how many cylinders are going to be operating? Is it a two-stroke, a four-stroke type system? Your engines are pretty much four-stroke. What you'll be, what you'll be testing and be working on. So you can have anywhere from 3 to 16 cylinders, and we'll talk about cylinders in just a little bit here. Cylinder arrangements, is it straight ahead? Is it in a V shape, an L shape, or it possibly could actually be in a pancake form, like some of your boxer motors that you have, like your Subarus and some of your older Corvairs, and also your VWs, the older VWs and stuff like that too. And then we talk about displacement. And that's where you start getting into the 2 liter, the 3 liter, 1.4, 1.2, and stuff like that. So I kind of went over that a little bit, but also we characterize it in valve train. How the valves are arranged. Or the overhead valve engine, do they have an overhead camshaft? Do they have a camshaft that's inside the block? I'll try to show you some examples as we go around through this section, and this may be multiple videos, just to let you know. So is it a spark ignition, like in your gasoline motors, your gaseous fuels, or is it compression ignition, which is primarily in your diesel side engines like that? And then what kind of cooling system does it have? Is it a liquid cooling system? Is it an air cooling system? We had in a few of our vehicles early on, we had air cooled systems like your older VWs, your Corvairs, and some of the less expensive Porsche machines too. So, and then a fuel type, is it gasoline? Is it diesel? Is it natural gas? Is it propane? And these are just some of the examples of the different types of when we go into configuration or classification. And then engine, can it be? Oh yeah, can it be? It can actually be located, in 3 different areas. Normally, the one that you'll see normally is going to be in the front part of the vehicle, where you're going to have the engine up front, whether it be straight ahead, or is it going to be sideways? So your transverse type mounts are kind of sideways there. Then we have, we had some is the mid mounted engine. So where it's actually in the mid part of the car, it's in between the passenger compartment and the rear, the actual, suspension, usually a transverse type mounted system on it too. Then there's the other one, the rear engine stuff, where you could have like Corvairs, VWs would have a flat or a boxer type motor that's mounted in the back. So there's all kinds of different configuration. I'm not talking about some of the ones that maybe somebody is converted and made into a specialty type system. I'm just talking about your everyday run of the mill type stuff. And this is, kind of what we have. And, you get some of the higher expensive cars, you may have a rear engine vehicle in that also. So the inline design is the most common, for the we had some old 3-cylinders that were in some of the early Geos in Metros and stuff like that. And some people loved them because they were, very fuel efficient, one, and they got great gas mileage, but they vibrated. You really had to have these balanced very, very well. And you could feel it as you took off. It was an unusual type feel to it, like that. And then you have, some of your vehicles like the 4-cylinders, straight inline type thing. And then you can actually have a 6-cylinder, and there are some 5-cylinders in some of the vehicles too. And 5-cylinders are not new. We've had them from way back when too. Now, back when I was early on, some of the Audis had a 5-cylinder in them and stuff like that. And then there's the V types. The V types, kind of common in the V6, V8, V10, V12, V16s. I've actually seen some V4s, competition type stuff out there. There will be a V type shape of the block, and that makes a difference in what the angle is at. When you get into your engine performance classes, we start talking about that, but this is just the basic overview. So you have your V type shit, which will have a cylinder head and a cylinder head. Now I do want to clarify too, because on the previous slide we'll talk about 4-cylinders. On the 4-cylinders and the 6-cylinders, you could have multiple cylinder heads, and that just depends on the actual design of the engine itself. But your V type, you're going to have, a camshaft, a cylinder head with camshaft, cylinder head with camshaft, and you can have multiple camshafts. You could have 2 camshafts, not uncommon. My 4Runner has a dual camshafts on both cylinders. It's a V6 type model too. And then of course you have the boxer type motors, or the pancakes, some people call them, and they were a flat motor. We still use them in Subarus, which is the most common now. Back quite a few years ago, we had them in the older VWs, and also the Corvair and some of the Porsches and like that. So, and then we want to get an overview of the basic systems on here. And we'll break this down in the next few slides to kind of give you an idea. So I like this picture right here because it kind of lays out a lot of the systems on the car. And when you're doing your inspections, you really need to be looking at all the systems. But your fuel system, like your fuel tank, all the way from the fuel tank to the pump to the filters. And this is just generic, so please don't take it as this is where everything is on your car or your customer's car. Then we have the fuel lines, and then we have the fuel, and actually a fuel filter. It goes up to a fuel rail, which then it goes to your fuel injectors. And then you have an intake system, where it be naturally aspirated or a forced induction type system. Then you have your cooling system, and then you have a charging system. And we go on back to the engine itself. Then we go into the actual transmission, which is part of the powertrain. Well, all of it's part of the powertrain. If you go from the engine back, and then if you have a rear-wheel drive vehicle, you're going to have a drive shaft. If you're wheel drive vehicle, you're going to have a couple of drive shafts. Then we go back to the differential, whether it be in the front or whether it be in the back of the vehicle. And then we come on down to the exhaust system. The exhaust system is very important because it takes the gases that have just been burnt and it puts them through a catalytic converter, which treats the gases to break them down to less harmful gases. And then we go back to piping into a muffler to keep down the noise, like that. And then whatever is left out of that has not been treated goes out into the atmosphere. So this is one of the things that we're really concerned about, is that output. What kind of output out of the tailpipe, and how harmful are those gases? And that's why we have the system called smog check. Okay, so cooling systems, parts of the cooling system, they're like the radiator. Then you have connecting hoses, which are rubber because you have to be able to flex a bit. And then you got heater hose, the heater core. You have one of the very important parts of the cooling system is the thermostat. And we'll be talking more about that as we go along here. But just to give you an insight, that thermostat is very important. Do not take it out of the system. If it's faulty, you want to replace it. And then we have a reservoir tank. This tank actually takes a little bit of the antifreeze and stores it. So when the actual liquid expands or contracts, it can be used. That recovery tank, it actually allows, when the fluid expands, to be siphoned into the recovery tank. And then when we cool down, we can actually contract the actual liquid, and then that liquid gets into the radiator again. And of course, we have the actual lubrication system. Some people don't know this, but the actual lubrication system is actually a big part of it, not just in reducing friction and keeping all the parts, lubricated and moving around, but it also is part of the cooling system. It takes a certain amount of heat away from the engine too, because it's in contact with all this heat. So this is something that people take in mind. And when you're not doing your oil changes on time, the actual oil can actually not transfer the heat as well. Plus, if you don't change oil on a regular basis, you can actually cause more friction to happen too. All right, so we also have the induction system, and earlier I said something about forced induction and naturally aspirated induction system. If you look at the first picture up front to your left, that is a supercharger, and this is going to be forcing more air into the intake system to have a bit of a better chance of more bang to the buck, you might say. Same with a turbocharger. This is actually belt driven or gear driven over here on the supercharger. This is actually, this one actually is a turbocharger. Pretty much all of them are turbochargers, but the turbocharger actually uses the waste exhaust coming out of the engine to actually power up this guy. So it's like free induction. And then you have your naturally aspirated systems. Now, these are the naturally aspirated systems have gotten much better. They used to be all super flat. These have actually running runners to the different cylinders, so that way they get the same amount of air as all the other cylinders do. And then talking about the fuel system, we have in modern cars, you have additional parts of it, not just the injectors, not just the fuel pumps and the filters and the tank. We also have the evaporator system. This is controls the evaporization of unburned fuel. So if you take fuel and you throw it down on the ground, that hydrocarbon is going to actually filter out into the atmosphere or raise up in the atmosphere. And that's one of the precursors of smog. So we want to have that system as tight as possible to make sure that we do not filter that extra gas, that hydrocarbon out into the air. So this is part of the system that controls that. So we're going to have, of course, a fuel tank pressure sensor. Well, I'll talk more about that as we go along through the different videos. And then we have the fuel tank evaporative control valve. We have an evaporative emissions canister. We have an evaporative emissions canister vent shutoff valve, and an evaporative emissions bypass solenoid. And then we have the evaporative emission control two-way valve that's inside of it. So these systems are very unique to the vehicle, and we'll talk about those more as we get into the emissions section. And then the exhaust system. This is the system that actually takes the inert gases coming out of the engine. So whatever's not completely burned goes out into the exhaust system, goes through the catalytic converter. And we'll talk more about the catalytic converter when we get the emission systems too. And then it goes through a muffler system, maybe a resonator type system too. We may have multiple catalytic converters on our car also, not uncommon. And then it goes out into the atmosphere. And then the powertrain, which includes the engine, the transmission, and actually the drive axles. And we've kind of covered all the different types of systems in the vehicle. Now I want to kind of break down some of the engine parts in the engine itself. I'm just going to use a 4-cylinder as an example. This is this is just an explorer view, and now this is before computers really got involved in it. So I just chose this because this gives you the basic. We'll talk more about variable valve timing and stuff like that as we go along, which is a little bit of a different system, which really helps with the performance and also the emissions too. So we have the cylinder head. We go on down to the cylinder head gasket. We'll have a cylinder head cover. We'll have the exhaust system on one side, and on this particular motor, sometimes you can have them stacked. And then you have the intake manifold itself, bringing in the air from the atmosphere. And then we come on down to the crankshaft pulley, on down to the engine block, down to the oil pan for the oil reserve for lubricating the motor itself. We have timing belts, timing pulleys, timing chains. It just really depends on what kind of system you have. And this is just the basic. When we get farther into it, we'll actually break down the engines even a little bit more. So these are two types of engine blocks. One is an actual gasoline, and the other one is actually a diesel engine. Now, I didn't put 2 6-cylinders up against each other, but you can see that the diesel engine, it has a lot of more weight to it. It's a little heavier constructed because of the way that diesel fuel ignites. We want to have more ability to control that combustion process. And we do that by strengthening up the diesel engines quite a bit more. Now on the engine 2, there is actually inside the engine block that goes up and down. And we'll talk about the combustion process in a minute here, but you can see there's two different, I want to show a comparison between the gasoline actually piston with the connecting rod attached. So this is the piston head right here. And then we have a piston pin that connects the actual piston and the piston, the actual connecting rod that connects to the piston. And this will go down into the crankshaft. We'll get into crankshafts on the next slide. On the diesel side, you notice the difference between the two heads on this particular one. Well, this is why, because the process, we're talking a lot more combustion on the diesel engines. And I'll break that down in just a little bit here. So on your crankshafts, and it really, it's one of the heaviest parts on the engine, besides the block itself. And it's there to actually help with when the piston actually moves up and down. It's going to give that movement, but we're going to take that piston going up and down and convert it from an up and down motion to a rotating motion. And when we rotate it, then we're actually taking that energy out to the back of the crankshaft, and it's going to connect to a transmission. I did find this actual crankshaft. This is out of an actual boat, or I should say a ship. It's not a boat, it's an actual ship. This is actually a person sitting in one of the crankshaft journals like this. And to work on these in the shipyards, you use a lot of heavy duty equipment to move stuff around. So I thought that was interesting. So then there's cylinder heads. This is the sealing part of the top of the engine that seals the engine block. And we have two different cylinder heads here. I have a single valve, two valve per cylinder, I should say, one intake, one exhaust. We'll talk about the importance of that. And then I have a diesel one here. You can see again, it's quite a bit of more metal to it. This is, 1 4-cylinder versus 1 6-cylinder, but you can see that the diesel on this diesel engine, we actually have 4 valves per cylinder and we have 2 valves per cylinder on here. And we'll show the importance of that in just a little bit here. We can have a 4 valve per cylinder also in gasoline motors also, or a 3 valve. It's not that uncommon. So let's talk about why and all that good stuff. So one of the things I want you to remember, and I'm going to go through the process of how we get those pistons to move up and down. All right. So, or side to side if you're a boxer type motor. But just think of it as the pistons going in a up and down type motion. So one of the things we have to do is to get the engine to run, we go through what they call a 4-stroke cycle. And just to give you a little bit of a background, the engine is it takes chemical energy, which is your air and your actual fuel, and it burns it to move it and to actually get it into motion, which is mechanical energy. Okay, so we're going to do a process where we're going to actually take air and fuel in the right amount, and then we're going to ignite it with a spark. Okay, so on the first part of the 4-stroke cycle, what you're going to do, the engine's going to do, is we're going to move that piston down. Okay, we're going to open up the intake valve. The intake valve is in the cylinder head. And we'll open that intake valve, we'll allow these piston to go down because that piston is sealed, that little cylinder. Now we're going to bring down that piston and we're going to draw in, and it really depends on what kind of motor you have. You could be drawing in air and fuel. You could be just drawing in air. We have, the direct injection systems, which I'll be breaking down in the engines class and a little bit farther on down in this class too. But we have air and fuel on this particular ones. So we're going to have air and fuel coming in from this direction, going down into the cylinder. And as that cylinder goes down, it's going to draw more air in that fuel supply. Okay, so it's going to be a certain percentage. So I want you to think of I want you to think of an actual perfect mixture to start off with, because we'll break down why it's not always a perfect mixture later on in the class. You have to have, well, to have complete combustion and to be the optimal mixture in a gasoline motor is 14.7 to 1. Okay, so that's 14.7 parts of air that we're breathing right now to 1 part of actual fuel. If it's a perfect world, and I'm going to tell you why that doesn't happen later on in the presentations as we go along. Well, we take that air fuel mixture, we bring it on down, and when we go all the way down to the bottom, so we're started at top dead center, which is what we call before top dead center, so DTC, okay, DTC, and then we're going to go all the way down to the bottom. We're going to go all the way down, okay, to the bottom. So, that's going to be where we're going to actually close that intake valve. And then we're going to compress the air and fuel. We're going to kind of heat it up a bit, okay? If we take molecules, if we were just kind of, playing around here and we had a little bit of gasoline over here, okay, this is fun. But I wanted to actually get it to explode, and we could get the gasoline to actually ignite and just sit there and flame, but that won't do me any good in an engine. What I want to do is take and compress it in that cylinder, okay? When I take and compress it in that cylinder, it gets all the air fuel molecules closer and tighter together. Instead of being all separated out, if I were to have, just kind of floating around here, yeah, I might get something to kind of ignite over here, but it would not go across here. We have to have a really good flame front going. We need that to propagate through. So that's why we actually compress it. Okay, we compress it really tight on a gasoline motor. We'll talk about diesel in just a little bit here. And then what we do when we get almost to the very top, we take and ignite that that cylinder. So that will actually cause a rapid burn of the air and the fuel, which all those pressures, okay, will actually cause it to slam that piston down. And that's where we get the power part. This is that power, or the combustion side, like that. And then we go over, because right now we have all the gas is burnt, all right? So the gas is all burned up on this process here. We have what we call inert gases, and this means it can't support combustion process again. So we need to get rid of that. So what we do is we've gone through the intake, we've compressed it down, then we've gone into the part of actually exploding, or having that rapid movement and burn of the fuel in the air, and we've caused it to cause that piston to be slammed down. And as it slams down, now we're going to go ahead and when we get to the bottom dead center, BDC, we're going to actually cause we're going to allow that exhaust valve to actually open up, so we can actually push as much of the air inert gas out, okay? And then we'll start the whole process over again. So again, we take an air fuel charge in, or just the air. We'll run that piston all the way down to bottom dead center. And then we go and compress that air. So this is the compression stroke. So we have an intake or an induction stroke. We have a compression stroke. Then we actually take and ignite the fuel as we get up all the way to the top. That causes the combustion process to go on, for the power stroke. And it causes the piston to be forced down. And then we go into the exhaust stroke. We actually open up the exhaust valve and we push the air fuel, the inert gas out. All right. So kind of breaking it down a little bit again, I want you to remember this. I want you to memorize this. So when the intake stroke happens, we're taking the piston, it's going downward, the intake valve is open, the exhaust valve is closed, and then the air fuel mixture enters into the combustion chamber. Then when we go into the compression stroke, the piston is moving upward, the intake valve is closed, the exhaust valve is closed. So you can actually see that both valves are closed right now. And then the air fuel mixture is compressed. So we want to have that great explosion going on. And on our power stroke, what we do is we have both the intake and the exhaust valves closed, but we're actually going to turn on that heat source. Okay, so in the and to get a fire to happen, which we want this to happen, we have to have air, we have to have fuel, we have to have some kind of ignition source. So you remember the old triangle of how things burn. You take one away, and then of course you are not supporting that actually fire. Afterwards, we actually take and open up the exhaust valve, and then we allow the piston to go up and take all the exhaust gases out. Excuse me, talking a little bit too much there. So now that we've talked about the gasoline or the spark ignition system, I want to kind of go through really quickly on the diesel side of the world. So on the diesel side of the world, same four-stroke cycle, okay? But we're going to take away the actual spark plug. And instead of just having a certain amount of pressure, just combined air fuel together, we're actually going to squeeze an air volume very, very hard. So let's talk about that. If we were to think back, okay, let's go ahead and go back a few pages. We'll go back a few pages all the way down to that one little diagram. And right, let's go back one more. All right, so let's take away the spark plug. Okay, that's what we can do right now. So we eliminate that spark plug. Now, instead of having a spark plug there, we'll have a direct injection injector, which is going to actually push in that air, push in that actual fuel, kind of at the last minute. So we're going to open up that intake valve. We're going to bring in just strictly air. We're not going to bring in any fuel at all. We're going to actually just bring in the air, and then we're going to squeeze the air on the compression stroke very, very tightly. On gasoline motors, we're probably talking anywhere from 8.5 to 1 compression ratio up to maybe 12 to 1 compression ratio. And we'll talk about compression ratios a little bit later on. But if you think of it as we're just bringing in the air, we're compressing the air very, very tightly. And we're talking anywhere from 16 to 1 to 22 to 1 on some diesel engines. And then when we get that really, really blazing hot, that's when we inject the fuel. So I take away the spark plug, and I'm going to put an injector in here instead. And then I'm going to take in the intake, okay, just air only. I'm going to compress it really, really tightly. And then when I go into the combustion cycle or the power side, I'm just going to inject fuel. I'm not going to have a spark plug. We're just going to inject fuel. And as I inject that fuel, that hot air volume is going to ignite that diesel fuel. We're going to spray it into a really tight mist. All right. So there's a lot of pressure going on here. And when that happens, it's going to cause that fuel to ignite. We slam that piston down just like we did in the gasoline motor. And then we do the same thing on the exhaust stroke. All right. So that is on the diesel side of things. All right, let's talk about the actual difference. Of course, we don't have an actual spark plug. We have an injector instead. All right, we still have an intake valve or multiple intake valves. We might even have multiple exhaust valves, but we do not have a spark plug. All right, let's talk about the combustion process. The power of the engine is produced to move a vehicle is the result of a series of chemical reactions between fuel, air, and heat. A mixture of fuel and air will react and expands. That's what we're trying to do. We're trying to get it to expand very quickly, but we want to propagate that flame front very, uniformly like that. This process is of combustion. This is the process of combustion. During the total combustion, all the fuel, if this was a perfect world, okay, we would have all the fuel and air burned, okay? It doesn't happen that way. Unfortunately, it doesn't happen that way. We have byproducts of combustion. And total combustion, however, can only occur if you have the proper ratio. Means you have enough fuel and you have enough air, and then we ignite it properly. We don't have some of the ill effects. And well, I'm going to talk about some ill effects of, I should say limitations, or what would be a better word? Let's say some of the effects of combustion that are not perfectly. We didn't burn all the air and fuel. So we have, things like cool temperatures, we have hot temperatures, and we want to have a perfect temperature of the engine to make sure we burn all the fuel as much as possible. If our spark isn't hot enough, if our spark is off timed, all these things can cause a lack of combustion, or a lack of complete combustion. Let's put it that way. So during the combustion process, fuel, which consists of hydrocarbon molecules, is broken down into the hydrogen and the carbon molecules, and this combined with oxygen, which draws through the air filter. And don't forget to keep that air filter in there. During the process, the air fuel ratio is correct. And then if we have a correct air fuel ratio, if we have enough oxygen and we combine it all together, we split things apart, then we can oxidize, consistently the heat, and we can oxidize it all and we would have a perfect combustion of CO2, and then we have a little bit of heat and a little bit of water. That would be perfect combustions. If I brought it in and it went perfect, my process would go out like perfect. So here's my little diagram on that for you. So if I have fuel, I have enough fuel, we have the right fuel mixture, we have the right oxygen, we have the correct spark at the correct time, the combustion process goes out, then we would have heat, then we have CO2, and then we would have of course we would also have a little bit of water going on. Actual combustion isn't that way, folks. We haven't got a perfect seal in the engine. There is a need for acceleration, deceleration, idle. All these things cause the mixture to not be perfect and the combustion process not to be perfect. So we want to have as perfect as possible, but we're getting close. Let's put it that way. And we have to fight another evil thing. It's called a nitrogen oxide, oxides of nitrogen. Anyways, if we get the temperature of the engine up to 2,500 degrees Fahrenheit or better, then we actually start combining the actual nitrogen with the oxygen, and it causes oxides of nitrogen. This is one of the precursors to smog, and this is one of the things we fight in the smog check program. So this causes that photochemical smog, that grayness you see out in the actual skies. This is what we're talking about. So we try to keep it at 14.7 as much as possible, and we do our best, but unfortunately we are still having a issue with that, and we have gases that go out like I said before, nitrogen oxide. We actually have carbon monoxide, not dioxide, but monoxide instead of the dioxide that we wanted. We have extra hydrocarbons, and those are the really good killers that we kind of try to combat. And then if you look at it too, carbon dioxide is one of the gases that would flagged as global warming. So these are all the things that we, as technicians, that we try to control, and the engineering tries to control as much as possible. That's why we have the smog related devices on your car. All right. So I kind of went over a lot of this stuff, so I'm not going to bore you again. So let's talk about, flame front travel. Although the combustion process is often thought of in a controlled explosion in the actual cylinder, it actually is combustion that's a slow burn process. And this is why, we'll get into it, why we like to use variable valve timing like that. That helps a little bit. So the combustion process cylinder takes about 3/1000ths of a second to burn. This is a relatively slow process. So, and gunpowder, does like, if you take gunpowder and you put it in a shell and a gun, it burns a lot faster. Let's put it that way. I think that's the best analogy right there. So normal combustion, we have the spark that occurs, we get that flame front going across. So here my spark happens, my flame front starts going across. Here it continues to go, and then we have the end of the combustion process. Boom, and we're all nice and happy. Let's put it that way. We get into pre-ignition. That's just one of the things that we also fight too. If we have one little, sharp object that maybe it got heated up during the process, get a little bit of carbon buildup, we can actually cause carbon to heat up too. And instead of having a flame front going across, here the spark plug goes up, and look at, we already have a firing going on. And then when they get together, they collide. And when it collides, it actually causes that pinging noise that we have going on. And then detonation, another, form. Again, we're, using this as a my picture here. I fired off, we're starting to go, but it actually has another, actually flame front going on. So detonation is another form of abnormal combustion, is often confused with pre-ignition. Detonation occurs when excessive temperatures in the combustion chamber cause a second source of heat source. And instead of just having that little glowing thing, we got too much heat inside the combustion chamber, and that can cause it to detonate. So your cooling systems are a great villain when it comes to that. You actually have to where if it's the engine's overheating, you're gonna hear some detonation going on. And detonation, even pre-ignition, can be very deadly to the engine. Let's put it that way. On top of smog, produced extra smog too. But we're talking about in pre-ignition, where you're actually taking and firing from a heated source. Well, that can actually cause engine damage. And in your detonation, and again, because we're overheating, we're causing that piston to get damaged, and we could have cylinder damage too. I've seen all kinds of holes in tops of pistons because of detonation. And then we have quenching. Quenching, that occurs when we have unburned fuel molecules, contact rarely cool surfaces. Over rich conditions can cause quenching. Leftover fuel that didn't get out on the exhaust side. Maybe you have a buildup of carbon, and the carbon was built up because of a lot of fuel, and now we have extra fuel on top of the carbon. Now it causes the flame front to cool down, so it doesn't propagate all the way through. So we start the spark, the molecules are getting cold right here, so we got a little bit of pooling going on, and then of course it stops the whole process. So again, we're taking extra fuel and putting it out into the atmosphere, well, through the exhaust system, which actually tries to process it, but it doesn't always happen that way. All right, so this is just a base. We're going to be breaking that down a little bit farther on. I kind of wanted to do an overview first, and then we'll break down all the other parts as we go along. All right. All right, folks, if you liked the video, please definitely make a comment down below. There is, it was kind of long-winded. I have other stories to tell about, the different parts of smog check and other engine classes and my engine performance classes. So please stay tuned and we will be back again. Like I said, if you have any comment, please leave the comments down below, or you can reach out to me through my email, or my students have my access cell phone number too. And if you like the video, let me know. If there's other videos you like to with this kind of content or something that you would like to see, let me know, and I will definitely create a video for you. All right, that's all I have for you right now. I'll see you in class. Take care now.